Welcome to another podcast. This episode we're going to be taking a look at sort of expanding on the idea of finding the area under the curve and introducing some more calculus elements to it, specifically something called a Riemann sum. So for this example, what I would like to do, and that's kind of what this whole video is going to revolve around, is I just want to try to find the area under the curve y equal x squared from x equals 0 to x equal b. And let's get a picture of this. So I'm drawing some axes here. And I'd like to, let me do a different color here. So this is the graph of y equal x squared. And we've got our limit here of b. And so we're going to look at trying to find the area under this curve. So if you recall what we discussed in the previous video, the very first step to this process is I need to divide the interval into rectangles. So I'm going to divide the interval into n rectangles. So I need to go along here and cut up into subintervals. That's what these are called, subintervals, and put a rectangle on each subinterval. So I've got rectangle, another rectangle. I'm choosing to use the right side of the rectangle as the height. So it's where the rectangle hits the function on the right. And I just kind of keep doing this process over and over and over again until I have a total of n rectangles. So there are n rectangles on this picture from 0 to b. So x is going from 0 all the way up to b. Okay, so that part's done. Now the second part is I need to sum the rectangles. Okay, now this is going to be a little tougher. If I want to sum the rectangles, I got to first kind of figure out what goes into a rectangle. So we look at the area of a rectangle. So the area is equal to the length of the base times the height. That's how you find the area of a rectangle. That's why we like to use rectangles, because they're easy to find. So what is the length of the base of each of these rectangles? Well, if it's over the interval b and I'm chopping it up into n parts, then the length of each part is going to be b divided by n. That's the length of the base of each rectangle. All right, what about the height? Well, the height of each rectangle is, because I use the right endpoint, you can clearly see here that the height of each rectangle is going to be governed by where it intersects the function on the right side. So the best way to go about this is just to kind of look at it in maybe a table for each piece. So here we have a table. We're going to look at different x and y values. So we're going to start with the very first x value. So the first one is b over n. That would be the first place where we would see a rectangle. So if n was 5, we would see it at 1/5 of the way to b. And then it would be 2/5, 3/5, and so on. So b over n is the very first rectangle's height. It's the very first rectangle's width, because each rectangle is width b over n. So the x value I want to look at is at the right endpoint. And what is the function value, or the y value, at the right endpoint? Well, because this is the function x squared, the function value is just b over n squared. All right, I've got to go another bn, right? So I've got my first rectangle, and I'm going to add another rectangle. So I've got 2b over n is the right endpoint of the second rectangle, and the height associated with it is 2b over n squared. If I have 3 rectangles in a row, then that's a length of 3b over n that I got to go to get to the right endpoint of the third rectangle. And that endpoint would give me a height of 3b over n squared. And we could keep going with this. The very last rectangle over here, its height would be, I have n rectangle, or excuse me, its right endpoint is I have n rectangles, each with b over n, so the right endpoint here is just b. Well, that makes a ton of sense. The right endpoint here is b, you can clearly see it, and what is the height's value? Well, it's just nb over n squared, or just b squared. So this gives me a pretty good idea of what this looks like. If I try to put it all into a sum, then you would say that the sum of the rectangles in this picture can be described as follows. It's b over n times b over n squared for the first one. So this is the, so in general, the height here, we're going to come back to this and try to fill in an arbitrary thing for the height. But I have it specifically for these values. So this is the, let's see, this is the base, and this is the height for the first rectangle. And if we do this over again, we get the base stays the same. The height is now changed for the second rectangle, and this would keep going all the way until we got to the last rectangle with height b over n, and we've already seen that it has nb over n squared total height. So that's the sum of the rectangles. Let's try to factor out and see if we can actually figure out what that sum is. I can see that every term involves at least a b over n cubed. So if I look at it this way, if I factor out a b over n cubed, then this first one is, when I factor that out, I get 1. Here, b over n cubed would leave the 2 squared. The next one would have 3 squared, and so on. The next to last one would be n minus 1 squared. And you can see this last one, if I take out b over n squared times b over n, that just leaves this n right here, and you get n squared there. So this is a better way of looking at the sum. And the question that we have to ask is, what is this value? What is the value of that sum? Now, there's many ways for me to figure out the value, most of which you're not ready to see. So let's just kind of talk about this geometrically, if we will. I want you to think of it this way. I'm going to take the term n squared to start with, and I'm going to think of a square that's n by n in width. So this is n units this way and n units this way. Then this has area n squared. So I'm thinking of the area here. What if I put another square inside of it? So this square would be 1 unit less. So it would be n minus 1 by n minus 1 in size, so n minus 1 on each side. And I just kept doing this until I get to the very top. And it's starting to look more like rectangles, but that's okay. I get to the very top, and so I'm stacking each of these sort of things, and at the very top I get something that is 1 by 1. So the size of this top one is 1 by 1. Well, if I think about the stacking here, then the area of the first piece is n squared, area of the second piece is n minus 1 squared, and so on until I get to 1 squared on the very top. And so if I think of this figure, this figure forms a pyramid. And so I can think of stacking blocks that are n by n up until they form this sort of pyramid, and we know that the volume of a pyramid is 1/3 base times height. And so even though this isn't exactly a pyramid, it kind of approximates one. So the base of this pyramid is n by n, or n squared, and the height of this pyramid is how many blocks we stacked up. So let's assume the thickness of each one of these pieces that we stacked up is 1, and I've stacked a total of n of them because my sum goes from 1 to n squared. So if I've stacked a total of n of them, this would be n for the height, if they each had sort of height 1. And that says that the figure that forms this is approximately n cubed over 3 in value. Well, if I go back to the equal sign here and continue on, then I have b over n cubed times n cubed over 3. Well, I get the n cubes to cancel out, and that gives me the value b cubed over 3 for this sum. Is that actually the area under this curve? Okay, well, let's think about that for a second. If I'm claiming to you here that the area under the curve is the integral of x squared dx, then if I use power rule for antiderivative, so if I compute the antiderivative of this function is x cubed over 3. And if I compare these two for a second, x cubed over 3 with b cubed over 3, I see a lot of similarities. And in fact, I see that x ranges over an interval of width b, and if I replace x with b, I can see this thing matches up really, really well. And so the question here is, do I actually have the right area? And this turns out to be the right area. This is the correct area for this particular integral. So if I took the area under this curve from 0 to b, I would get b cubed over 3. Now we're not quite ready to actually do the antiderivative operation to come up with that, but I at least want you to I at least wanted to show you using these sums that this what this sum limits out to. Now the only part of this that should cause you some maybe consternation is this approximate thing. And so the only thing here that is approximate about this is I only have n terms. The idea is if I take the limit as n goes to infinity, this is actually equal to n cubed over 3. So this is where the calculus part sorts of enters into the equation. Is I've got to take, and this is the third step, right? So we've done our first two steps. The third step is, can you imagine that this pyramid that we formed here, if I increased the number of levels to infinity, then each level gets less than, and it still takes up the same amount of space for the pyramid. Can you imagine that in the limit it actually gives the answer n cubed over 3? That's what we have to sort of figure out here, is if in the limit we get b cubed over 3. Now, the best way to sort of handle this is by developing a sort of better notation for all of this. And so that's what I'm going to focus on now. So let me create some space here. I don't want to get rid of my sum just yet. So let me create some space there. And we'll just kind of do this in this middle section here. All right, so recalling the sum of the rectangles that we have here, we're going to look at something called a Riemann sum now. Now we want a better sort of notation than to just try to string out the sum like this. So here's what I want you to see. This describes the first rectangle, I equal to 1. This describes the second rectangle, I equal to 2. This describes the nth rectangle, I equal to n. And in mathematics we have a sigma notation or a sum notation for that. And the notation that we have is that this sum of rectangles, so if I want to kind of go on a different path here, the sum of the rectangles for this problem is equal to, our notation mathematically is this: I goes from 1 to n of, you can see here that the base of every single one of these is b over n. The width of every rectangle is the same, so it's b over n for the widths. So this is the width of the base. And then the height is changing based on which rectangle it is. So the first rectangle has a height of 1b over n. The second rectangle has a height of 2b over n. The third one would have a height of 3b over n squared. All these are squared. And so in general, which rectangle we're on determines the number for the height. So it's ib over n squared. This is the height of the ith rectangle. Now, That's all well and good, but we want a more general form. So that's kind of where we're heading now. More generally, let's suppose that this is not the picture anymore. So let me kind of go back, clear up some more space. Let's suppose that I want a more general problem. My more general problem is this. Let's find the area under the curve y equal f of x between the points x equal a and x equal b. Then for that particular problem, our graph's going to look a little bit different, but there's going to be some similarities here. So we've got graph, we don't know what it's doing. We don't really care at this point what it's doing. We start at the point A, we go to the point B, and we simply want to describe the area under that curve. So this is the curve, y equal f of x, and we want to describe its area. Well, I'm just going to think about an arbitrary rectangle here. And, I don't care where I put the rectangle. I just know the height is wherever it intersects. So I'm going to suppose that it intersects at the point CI. So this is the height of the ith rectangle is the function value at CI, so f of CI. It could be the right endpoint is where it intersects, which we showed on the previous. It could be intersecting at the left. It could be intersecting in the middle. We don't care. We don't care where the intersection is. Under this picture, the idea is the width of the rectangles. So if we wanted all rectangles to have the same base. So it was b over n for all of them to have the same base on the previous thing. Then that base we're going to call delta x, because we've come to know delta as being a width. So delta x is the width of the base, and here it would be b minus a over n if we wanted n rectangles. So if we wanted n rectangles on this interval, each rectangle would have width b minus a over n. Remember on the previous one it was b minus 0 over n. So we really haven't changed a whole lot here. But we're going to call this quantity delta x. We know that the height is f of ci. And so if we tried to just generally write this sum, so the sum in this case is equal to use our sigma notation, I goes from 1 to n of, well, it was the width of the base. The width of the base here is something called delta x. So we'll go ahead and put that in here in a second, but here was the height of the ith rectangle, and here we're saying the height of the ith rectangle is ci. Okay? Then we have the width of the base, which we're calling delta x. So this is now the sum of the rectangles. This is the general form that the sum of the rectangles takes. And what's interesting about this is if you take the limit as n goes to infinity of the sum of these rectangles, then this is our definition of the integral of a over b of f of x dx. So this is called the definite integral, and this is called its Riemann sum. And so one of the most important things in the course is that you understand this relationship. If you do the limit of this process that we've been talking about here, so the limit of this process, that ends up being the integral as we define it. In fact, the integral symbol itself, it kind of looks like an S, right? So in modern day, we think of the integral symbol like this. So this is sort of modern notation. The integral symbol used to be more like this. So this is kind of an older notation, and it literally stood for S equals sum. So we literally think of this as being a limit of sums that is itself a sum. And so the integral from a to b of f of x dx we call the definite integral, but it is a limit of these sums. And the sums that are formed are called Riemann sums, and they're always of the form delta x times the height of the function at several different points. All right, this has been a sort of introduction to what the integral represents, where it comes from, and how it can be calculated. But I want you to understand this is not how we're going to calculate the integral. And this is a good thing, because for a different function, this sum over here that we tried to calculate earlier, this could be a very, very difficult sum to calculate. Here we couldn't even really calculate it. We sort of had to estimate it to show that we got the right answer. All right, we're going to talk more about sums in class, but I just wanted you to take a look at this example to get familiar with some of the notation and some of the arguments, and we'll try to clarify some things in class. All right, thank you for watching.